Hello, hello, hello. So welcome to your first online lecture. So this is the setup I'm going to be using. So you can see my hands, you can see the paper. I'll be moving it up and down as we lecture. And of course, just as taking an online physics course is going to be a learning curve for you, so is teaching an online physics course that started out as an in-person physics course will be a learning curve for me. So I have designed online physics courses before, but they were always classes designed to go online from the very beginning. All right, so I'm really glad we finished up with RC circuits last time in class, so we can just start chapter 20 just fresh and new today. So chapter 20 is going to be all about magnetic force. So we've talked about magnetic fields, we've talked about electric field, and now we're going to start this really exciting buildup where we're going to be bringing some stuff together. Chapter 21 or 20, 21, and 22, I just think these are some of the most exciting chapters that I get to teach in the introductory physics sequence. All right, so to do this, we need to recall a couple of things. So recall magnetic fields are associated with moving charges. And we calculate them. B is equal to mu naught over 4 pi Q V cross, oh my goodness, that's a bad cross, R hat over R squared. So that's, and the magnetic field contributed by small current elements is delta B is equal to mu naught over 4 pi current I, that's conventional current I, delta L vector cross R hat over R squared. So, and both of these come from chapter 15. So, if you need a refresher on magnetic fields, just review your notes from chapter 15. Speaking of notes, I hope you're taking notes along with me today. That's going to be really one of the best ways to get the most value out of this online experience. Okay, so magnetic forces on a moving charge. So we know that moving charges make magnetic fields, but we haven't talked about what happens when you put a moving charge through a magnetic field. So there is a 3D relationship between direction of magnetic field on a moving charge and the direction of the magnetic field direction of velocity of moving charge and the sign of the moving charge. Okay, so all of these things have been found through theory and experimentation, which give us a brand new equation for us to add into our arsenal. So, magnetic force. The magnetic force is equal to the charge Q times the velocity V crossed with the magnetic field. So we can see once again we're using a cross product, meaning we're going to get a vector solution, and this is just scalar multiplication. So Q is the charge. It does include sign. So what is it, a proton? Is it an electron? This matters. V is the velocity of the moving charge. And B is the applied magnetic field. So this is a charge that is going through a magnetic field. So remember, B has units of Teslas, which are equal to newtons over coulombs meters per second. We can also write that as newtons per coulomb over meters per second. And we can see that this unit nicely falls out from this equation. Beautiful, eh? Okay, so when you're doing these types of problems, use the right-hand rule liberally to verify direction. So remember, you line up with V and curve, let's see. Line up with V, curve towards B with this case, or like that. And your thumb, here's your thumb. This is going to be the direction. So quick antecedent, so I see where's your thumb, and it makes me think of Esther, who has just learned that classic song, where is the man, where is the man, here I am, how are you today, sir, verifying field, sir, run away, run away. See, I told you I'd try to add some humor into this. I hope you appreciated that non-academic antecedent. Okay, so one thing to note, twice apparently, is that for electrons, Q is equal to minus E, which implies magnetic force on the electron is opposite to the direction of V cross B. So basically, if you've got a negative charge, you get your direction for V cross B, and then you reverse it. Just like the Missy Elliott song. All right, so what does this all mean? It means that I'm talking alone in a room is what this means. So magnetic fields deflect charged particles. So if a particle goes through a magnetic field, it's going to change direction in response. So let's say got a magnetic field over here. There it is, pointing towards you. You got an electron. It's just, chilling. It's got some velocity V, and it's going to get closer and closer to this magnetic field. Oh my gosh, there it is. And it's going to curve its direction. So the force is going to be equal to minus E V cross B. So essentially, this is the implication. If you send a charged particle near a magnetic field, it will change direction because it will experience a force. It's like physics 1 is still important. Okay, so what about, what if a charged particle is not moving? So V is equal to 0. Well then, and it's in a magnetic field. And in B field, nothing happens. If we look at this equation, it must have velocity in order to experience the force of the magnetic field. Otherwise, it's just, well, I'm just going to hang out here. You turn up that magnetic field as much as you want. So what about electric fields on non-moving particles? Well, we can think all the way back to when we used to see each other in chapter 13, and of course it has an effect. Still impacts. So basically, electric fields always impact charged particles. Magnetic fields only impact them if the particle is moving. So what would be the application? So here's where I would normally ask you, but now I'm just going to tell you that, of course, the application is accelerators. Accelerators use magnetic fields to move particles around. So they take advantage of, they get the particles moving, and they can change their direction by putting them through different magnetic fields and have them experience a magnetic force. Okay, so let's think about our equation a little bit more. QV cross V. So I have to remember that I don't still have stuff written up on the board. All right, so if we look at this equation, you would expect a magnetic field if you move a charged tape over a magnet. So that would certainly happen. So move charged tape over magnet, magnetic field. Because you've charged up the tape and now you're moving it through a magnetic field. Now, of course, the charged tape will polarize the metal, and it actually makes the electric field stronger. Okay. And in that case, the electric field is actually going to be the predominant force. So this isn't really the best example, so let's move on to a different example. And hopefully some of you still remember what these are. I'm really wondering when we get a new edition of this textbook and they realize that nobody knows what a CRTV is. Because CRTVs used this equation to give you television. Of course, it's like those old beefy TVs, so perhaps you saw these in your childhood. These are still around when I was in college. I owned one. I got it on clearance at Radio Shack. No, not Radio Shack. Circuit City, a now defunct chain, because everyone was moving to plasma screens. So this is a CRTV. By the way, that TV lasted me forever and ever and ever. So this is a cathode ray television. We still use cathode ray tubes in physics experiments, by the way. But basically, the way these would work is they would accelerate electrons to very high speeds with electric fields, and then they would deflect them using magnetic fields. So accelerate electrons with E fields and deflect with B fields. So, and in this case, you're going to be dealing with much more significant forces than if you were to just wave some charged tape over a magnet. So, to really understand why these are so different, why they could really get significant deflection, we need to return to our equations. So there's some really important relationships we're going to be joining together, Physics 1 and Physics 2. So acceleration, as I hope you all know, is the change of velocity with respect to time. Of course, remember, you can always be thinking in terms of deltas, although I'm going to stick with the calculus expressions. All right, so acceleration is equal to dv dt, and this happens to be proportional to the charge of a particle divided by its mass. So remember, we did some stuff in chapter 13 that kind of hinted at this. So force magnitude is equal to the magnitude of the change of momentum with respect to time. And we know that the magnitude of the force for the magnetic field, we can express the cross product in terms of the magnitude of V times the magnitude of B times sine theta of the angle between them. So that will give us a scalar response. This works, of course. And we can now think about this in terms of acceleration. So this is equal to dv dt, which is equal to q over m, v, b. So I'm going to drop the magnitude and simply denote these as scalars by not writing vector signs over them, sine theta. Of course, in this case, v is much, much smaller than c. So we can see that this ratio here will determine the acceleration. So the magnetic field is what it is. The velocity is what it is at a given point, and then it's going to change. This is going to scale that. Okay, so let's do some comparisons. So, by the way, a really cool experiment you can do in a modern physics lab is you can look at the charge mass ratio for a single electron. You can measure it. It's a very cool experiment. I think it's the Millikan oil drop experiment. So 1.6 times 10 to the minus 19 coulombs divided by 9 times 10 to the minus 31 kilograms is approximately 1 times 10 to the 11 coulombs per kilogram. Now, the charge per mass for charged tape, of course, this is an estimation. So we've previously estimated having a charge of 1 times 10 to the minus 8 coulombs divided by 1 times 10 to the minus 4 kilograms, which is approximately 1 times 10 to the minus 4 coulombs per kilogram. So we can see this is a lot bigger than this by several orders of magnitude. So this is going to have much larger acceleration than this, which is basically not going to be noticeable. Okay, so moving on, what this is building towards is that you can use magnetic fields to get circular motion of charged particles. If I can spell circular, that would be great. Also known as helical, or sometimes helical. Okay, so let's dissect this in more detail. So, you've got your electron, you've got your magnetic field, there it is. It comes in, straight path, and then it curves, and the path gets straight again. So, straight, straight, curved. Okay, so it's the deflection that curves it. So when you get magnetic field deflection, so pretend, I feel like I might need to exaggerate this, so. Oh, that's even worse. All right, okay, ignore that drawing. Okay, so it's straight until deflection, and when it's deflected, magnetic fields direct electrons in a curved path. This has been measured extensively through experimentation. So now we would need to think, what if we had a larger region of magnetic field? So you could get your electron to come in. Now you've got a big magnetic field, and now all of a sudden you've got this going on. It's going round and round and round, like a record baby, right round, right round. So one example of this is the Northern Lights. So there you have all of the charged particles that are in our atmosphere, And you've got the Earth's magnetic field, and it causes them to go around, and you get a beautiful picture show that is simply the result of the circular motion caused by the magnetic fields. Oh, that is Northern Lights. Okay, so I think these YouTube videos are going to document what a terrible speller I am. In circular motion, so let's say you've got V, you've got your magnetic field here, and your force is perpendicular to EV, so this is a proton, cross B, plus E proton. So in this case, we can see no work is being done by the magnetic force because it's perpendicular. And so it's changing the direction of the particle without a change to speed. So this will change direction without a change of speed. So it is required that you have these two things be perpendicular. So basically, this happens when a particle moves horizontally. And there's a lovely 3D image in your book. I'm worried I will knock my setup over if I bring it in, but I'm hoping that you use these notes in conjunction with your book. So otherwise, if you don't have something moving horizontally, then you get this. And so that would happen where you've got a couple of different a different angle coming in. So you get a spiral helix. And depending on what you're going for, this could be absolutely right. But in both cases, you're still dealing with circular motion. So circular motion is circular motion no matter what the cause is. Okay, so moving right along. So we do have some equations to describe circular motion that we did back in Physics 1. So think back to last semester when we got to see each other more often. And so I feel like if I was one to take the time to edit, I would put in a meme from the Titanic. So recall Physics 1 to a particle traveling in a circle. So it has got some radius r, and it's traveling at constant speed. Okay, so we know that the force is equal to dp dt, which is equal to p v over r, where p is equal to gamma mv, which is equal to mv over the square root of 1 minus v over c squared. So this is the most precise definition of momentum. Okay. V over r is angular speed. Otherwise known as omega. Omega has units of radians per second. You'll often see omega written with units as 1 over seconds. So momentum v times r is equal to omega times p times momentum, which is equal to omega gamma mv. So that is the precise definition, works for all velocities. Now, let's use our friend And this is a friend you can use. It's the momentum principle, of course. Which relates force is equal to the rate of change of momentum, or we often do rate of change of momentum is equal to F delta T, doesn't matter. And now we're going to bring this to play with our magnetic force, which I think I can fit here before we start over. So this is QV cross B. So we're going to have all of these equations play together. They're not quarantined. I don't know, is it too soon to make jokes like that? We'll see. Okay, so F is equal to QV cross B. So we have omega gamma mv is equal to QV cross B is equal to QVB sine theta. So we would need to keep the magnitude of Q there since we are working in terms of scalar products. So remember, we had just previously derived this for force. And so we can use this to go after omega. And so omega is equal to QB over gamma times m. And because this has our gamma factor, this is valid at any speed. You can always use that equation. Doesn't mean it's always the best choice to use that equation. Remember, we don't make our lives harder than they need to be, especially right now. Now is the time for good humor. So for low speeds, which happens to be a brand of ice cream, amazing, gamma is equal to approximately 1. So therefore, omega is approximately QB over m. So we can also derive this relationship using the momentum principle. We'll go ahead and do that. So in other words, this is just another way to do this derivation. So we have dp dt is equal to p v over r, which is approximately v mv over r, which is equal to mv squared over r. We saw this in Physics 1. So dp dt is approximately m dv dt, which is equal to f net. So m v squared over r is equal to q over vb sine of 90 degrees in the case of horizontal motion. So m omega is equal to qb or omega whee. So this is circular motion where it's that one situation we first talked about. So not the helix, but just constant speed going around a circle. Nice perpendicular motion. Omega is equal to QB over M. So same thing here as we got up here. So pick your poison, either of them work. All right, so now we need to put a little bit of time into this equation. And by the way, since you like to know when I remind myself that I made a joke, it's written in my notes right here. Ha! I made a joke. So, time. The times there are changing. T is the time it takes for a particle to complete an orbit. So it starts here. We want it to get all the way back to here with none of that artistic nonsense or lack of artistic nonsense. Okay, so angular speed, omega, is equal to 2 pi over t. Think back to physics 1. And omega, as we just derived, is approximately QB over mass. So therefore, 2 pi t is equal to QB over m. T over 2 pi is equal to m. Q times b. T is equal to 2 pi mass divided by Q B, which I can now show you. All right, so notice something very interesting about this relationship that does not depend on R. So basically, the time around is determined by the magnetic field for a given particle. And so what happens is if you increase the velocity, it's going to keep that time the same. So notice there's no velocity component in here either. So there's no v, there is no r. And so what happens if v gets bigger, it will compensate by doing a bigger orbit to keep t the same. Pretty cool, huh? And yes, this is exploited for technological purposes, as we exploit, hopefully, all good knowledge. All right, so further, if you know the magnetic field, so if you know B, and you know Q, you can find the momentum by measuring R. So dp dt is equal to P V over R is equal to Q V B. P is equal to Q B R. And by the way, this is actually true for any speed, including relativistic speeds. And we use this in high energy particle physics, otherwise known as the HEP field. By the way, I was a part of the HEP field as a dark matter detector developer for some strange reason. All right, so speaking of accelerators, let's talk a little bit about them because I think they're very cool. So there's this longer section in your book, but I wanted to say a couple of notes about particle accelerators just because, you know, I've worked with a lot of people who've worked on the LHC. I used to do laser wake field particle acceleration. They're just kind of near and dear to me. So particle accelerators come in different breeds. So you can have typically related to what types of particles they're accelerating. So you can have proton accelerators, and electron accelerators. So I did electron acceleration at the laser lab. So which do you think requires more energy? Let's think about that for a second. Protons weigh a heck of a lot more than electron accelerators. So protons are definitely the more challenging beast to get moving around. And they have a very important application. So proton acceleration is used to study nuclei. Study nuclei. So, as protons, protons will repel positive nuclei, because nuclei are positive. You need really high acceleration. So you got to get them whipping around as close to the speed of light as you can. Obviously, they can't get to the speed of light because, resources are limited. Namely being you don't have infinite energy. And to get that really high acceleration, you need a really big magnetic field. Okay, so if we recall to the recent past, omega is equal to Q B gamma over M, so this depends on V. And so for the LHC, to get particles accelerated up to where they want, they're using B fields as of the time your book was published, now they're even bigger, up to 8.4 Tesla, which is pretty big. So I used to work in a lab with a 1 Tesla magnet, and we had to use safety precautions around it. So Tesla is a really big unit of measurement. All right, so that wraps up our section on circular motion and magnetic fields and the magnetic force and our fun little accelerator talk. I really recommend reading a little bit more about accelerators. Very cool stuff. And now you have some of what you need to start understanding them, or more of what you need to start understanding them, because you already have some stuff. So magnetic field force on a current carrying wire. So we've talked about big scale applications. Now let's talk about small scale applications. Okay, so we might be interested, in fact, you should be interested, on how a magnetic field impacts a circuit where we've got lots of moving charges. And this is something, particle accelerators, they take a lot to build. Circuits, easy peasy, you've done it many times. In fact, my daughter can build a circuit. But she can also tell you what a neutrino is some days. So we got a whole bunch of moving charges. Okay, so let's start drawing our little wire. So we've got a section of wire. Once again, I have just some excellent drawing skills here for you. So you've got some cross-sectional area A. You've got some drift speed. There's some velocity. Your magnetic field is coming out. And it's traversing some delta L, and you've got some charge density. So the number of charges per meter cubed. So we're all familiar with what is entailed in a wire. All right. So using that idea, we can calculate the magnetic field on the charges, the moving charges. And just to note, we are sticking with conventional current because of Ben Franklin. Last year I had somebody in my class who was the daughter of an engineer, and she had many things to say about conventional current. I really enjoyed that. So we assume positive charge. We incorrectly assume positive charge. But remember, it doesn't matter in terms of a calculation. So and by the way, this isn't just an American thing. This is a physics thing. So what do we have? Because I would assume someone would be like, well, what about metric and English standard? Like, no. Physics is just decided as a field to be wrong. So thinking back to the drawing that we just had up, that we have V bar, which is drift speed. Delta L, so which is going to lead us, we could get volume of some length. And of course, the vector is going to point in the direction of velocity. Got A, which is the cross-sectional area. And we have NA delta L, which is moving charge per unit volume. Okay, so we're going to use this. We're going to go after magnetic field. So let's go after magnetic field. I mean, what else did you want to do today? Binge watch something? Psh, way cooler to go after a magnetic field. You can tell your little sister that's what you did today, if you have one of those. So there are NA delta L moving charges that will be impacted by a magnetic field. So now we see why we took all the time to talk about circuits. So now all of these things just come easily to you. So the total force on the wire is NA delta L Q V cross B is equal to QNA V bar times delta L cross B. So we're just putting a bunch of stuff together that we already know. I'll try to leave this here. So if we recall, V is equal to V times V hat. So it follows, which is a movie I've not seen before. V delta L is equal to V hat times delta L, which is equal to V hat delta L, which is equal to V delta L. All right, so also recall conventional current is I is equal to Q N A V bar. So the magnetic force can be expressed as I delta L cross B. So in this case, building on our previous expression of Q V cross B, now we're looking at the sum of several charges added together. So this just falls out of doing a sum approach. And